Welcome to The Explainer. Today we're going to completely demystify something that looks like it belongs straight in an advanced engineering lab. We are breaking down the complex-looking schematic of a 1,000-watt high-power induction heater. If you've ever wondered how electrical engineers map out systems capable of generating literally extreme temperatures, well, you are absolutely in the right place.
It's truly fascinating to think about how a static, two-dimensional diagram of standard off-the-shelf electronic parts translates into intense metal melting heat. And it does this without any direct physical contact. Seriously, think about that for a second. How exactly do we take basic components, hook them up to a power supply, and pump out 1,000 watts of raw, invisible energy? That is the exact puzzle we're going to solve together today.
All right, let's just dive right into this diagram. Now, at first glance, I know it kind of looks like a bowl of brightly colored electronic spaghetti. You've got lines running everywhere, all sorts of different shaped components, dense technical labels, but I promise you, by the end of this explainer, you're going to see that this is actually a beautifully elegant and highly organized system, designed with a very, very specific purpose.
So here's our game plan for today. 1. Decoding the 1,000-watt heater. 2. The resonant heating core. 3. Current management and chokes. 4. The MOSFET power switches. 5. Gate control and safety. And finally, 6. The complete system visualized.
Okay, let's kick things off with Section 1, decoding the 1,000-watt heater and figuring out how to actually navigate this schematic.
The brilliant thing here is how it illustrates the path of the current using specific colors to guide your eye right through the power and control pathways. Notice how those bright red traces clearly flag the positive incoming power. Meanwhile, the stark black lines represent the ground or the negative return paths. And the blue, green, and purple lines, well, those are our intricate signal and control pathways bridging all the heavy lifting components together.
Now, look closely here. Notice the push-pull symmetry? If you were to draw an imaginary line right down the middle of this diagram, you'd see that the left and right sides perfectly mirror each other. We have a specific set of components on the left and literally the exact same set over on the right. And this isn't just to make the diagram look pretty. This mirrored design is fundamental to how an induction heater actually operates. But for us, from a learning perspective, it's a massive advantage. If you understand the flow of electricity on the left side, boom, you automatically understand the flow on the right. It instantly halves your mental workload as we analyze the circuit.
Moving right along to Section 2, the resonant heating core. This is the ultimate output of our system. Draw your eyes up to the top left corner. That prominent copper structure and those black rectangular blocks right next to it. That is where the actual induction takes place. Literally everything else in this entire circuit exists solely to serve this one specific section.
Let's look at the specs that define our resonant core. We've got a heavy-duty 6mm thick copper coil wrapped into 6 turns. Connected directly across it is a massive capacitor bank made up of 6.33 microfarad 630-volt capacitors. Together, the coil and the capacitors form what's called a tank circuit. They rapidly pass energy back and forth to each other, kind of like a high-speed game of hot potato, creating this intense oscillating electromagnetic field that will heat up any conductive metal you place inside that copper coil.
Which brings us to Section 3, current management and chokes. Taming the power.
Sitting right behind the core and feeding directly into it are these 2 copper-wrapped donut shapes. These are 100 microhenry inductors, rated for a whopping 10 amps each, and as you can see, they're tied directly to that red positive power line coming up from the bottom of the diagram. So what's their job? The crucial point is that these inductors, often referred to as chokes, act exactly like electrical shock absorbers. Because our resonant core is oscillating at incredibly high frequencies, it desperately wants to send that chaotic, high-frequency alternating current backward, right into our delicate direct current power supply. These chokes step in and say, no way. They allow the smooth DC power to flow in, but completely block the high-frequency AC from escaping back out.
All right, let's head to Section 4, the MOSFET power switches, the brawn of the operation. Right front and center, you'll find the beating heart of our push-pull system. These are 2 large, 3-legged chips labeled Hobman IRFP260N. Because we have that mirrored symmetry we talked about earlier, these 2 chips act together as a perfectly balanced team.
Now these chips are MOSFETs. They are highly efficient, solid-state electronic switches. Their entire job is to rapidly switch massive amounts of power on and off, alternating between the left side and the right side thousands of times every single second.
By taking turns pulling current down to the ground, they're the ones creating the very oscillation that drives that copper induction coil we were just looking at.
Let's step into Section 5, Gate Control and Safety, the brains and the support.
So this table right here is basically a cheat sheet for the brains of the operation, the smaller passive components surrounding the MOSFETs. We've got large 5-watt, 470-ohm resistors dropping the main voltage down for the control gates. We have 10K resistors ensuring the gates fully turn off when they're supposed to. We've got 12-volt Zener Diodes acting like strict bouncers to ensure the control voltage never ever exceeds 12 volts, because that would instantly fry the MOSFETs. And finally, FR307 fast recovery diodes controlling the exact timing of when each side fires.
Actually, let's trace that purple control path step by step just to see how these safety components sequence the timing so perfectly. The purple line delivers the turn-on signal to the left MOSFET. Instantly, the 12-volt Zener diode clamps that signal to a safe voltage. The 10K resistor just sits there, ready to drain the signal away the millisecond it's time to turn off. Meanwhile, the FR307 diode cross-connects over to the opposite side, essentially yelling, "Hey, I'm turning on now, so you need to turn off." It is just a flawless, high-speed mechanical dance executed purely through solid-state components. Oh, and we absolutely cannot forget this simple yet incredibly vital pathway at the very bottom of the schematic. It taps into the main red positive power trace, routes it through a small 4.7K current-limiting resistor, and uses it to light up our green status LED. It seems like a tiny detail, right? But when you're dealing with 1,000 watts of invisible power, having a bright green light screaming, "Hey, the circuit is live," is an absolutely crucial piece of safety engineering.
Which brings us to our final part, Section 6, the complete system visualized, going from spaghetti to blueprint.
Look at our original diagram again. Notice how your whole perception of it has completely shifted? What once seemed like an intimidating, chaotic tangle of wires is now a highly readable map. You can clearly see the DC power rushing in, being managed by the chokes, rapidly alternated by the heavy-duty MOSFET switches governed by their safety gates, and finally, just slamming back and forth inside the resonant coil and capacitor bank to generate immense heat.
It really comes down to this thought right here. A static diagram translated into a beautifully orchestrated, mirrored engine of intense, resonant heat. It's incredible how effectively this systematic, color-coded layout demonstrates complex electrical engineering in such a raw and accessible way. Every single resistor, diode, and capacitor plays an essential, highly specific role in keeping this mirrored engine running smoothly.
But you know, that brings up a really fascinating engineering question. If this perfectly balanced layout easily handles 1,000 watts, what is the weakest link? What specific component in this diagram limits this from becoming, say, a 2,000-watt circuit? Is it the thickness of the copper coil? The voltage rating of those capacitors? Or maybe the maximum current of the IRFP260N MOSFETs? I'm going to leave you with that provocative thought to ponder. Thank you so much for joining this explainer, and keep exploring.